And hello, welcome YouTube to this video on OpenFoam again. So last video we were talking a little bit about boundary conditions. Yeah, just check the volume. Okay, volume's working. Yeah, on last video I was talking about some boundary conditions. One of them is one of the less common ones is this thing called flowRateInletVelocity. And if you're interested, I have these videos, these links will be placed in the description below, and these are standard templates for how you can use this boundary conditions. One of them is this flow rate inlet velocity, where you can specify the volumetric flow rate, and they say here it's in meter cube per second, or of course you can specify the mass flow rate as well. But over here I use volumetric flow rate, so that will be my the way I specify the flow rate. Of course you can use the mass as well, and the mass flow rate will be in kg per second. Okay, and then you will have to provide some kind of density, of course. So over here it will be this density. Okay, you will provide the flow rate here, and that will actually correspond to the velocity of this inlet profile. Okay, so this is you can read up about how to use this over here. These are standard template files. You can just put it in yourself. It's pretty straightforward. You just follow the templates over here. See patch name, and you have to specify the type. Remember your semicolons. Volumetric flow rate, extrapolate profile, yes or no. So if there's no extrapolation of profile, it will be a plug flow, and this value will be the initial value. So it's an initial guess of the velocity profile. So it will only be used at the first iteration. After that, it doesn't really matter anymore. Okay, so don't be too confused when you see this value here. Okay, so that value is only the initial value, just like how you have this internal field being this when you specify internal field, the uniform 000 just represents the initial numerical guess of this velocity field, nothing more. Okay, so that's what we have here. Okay, so we have outlet shell, inlet shell, and that's defined for you. Now the more interesting thing is, of course, this external wall heat flux temperature. If you are not sure, what boundary conditions there are to use, you can use for temperature. So I will just use a new terminal under File, New tab if you are using Linux Mint, or Ubuntu. I believe there's something similar, but Windows subsystem for Linux, you may have to use the Windows terminal. Yeah, there should be some nice software coming up where you can use multiple tabs, or else you have to open a new window. Okay, anyway, again, it's CHT multi-region foam. Okay, list scalar, this scalar boundary conditions, list scalar BCs. You will have all of these pop up, and what I'm looking for is you see this thing here, external wall heat flux temperature. That's one of the ways you can do this. You can emulate, some heat loss or heat gain. And okay, so that's one of the ways. Then for other ways, you can actually see, I think there's a wall heat flux somewhere, wall heat transfer, where you can specify a wall heat transfer flow rate. So these are really different ways you can do it. I'll just go through the external wall heat flux temperature, but before that, let me show you the link. Okay, so there are a few ways you can again do this. Okay, there's this thing called convective heat transfer. Okay, anyway, this blog is by Fumiya. Looks over here. And according to this blog site, he's a CFD engineer in Japan. Okay, and there's some good documentation over here. Alright, so there's one called convective heat transfer. So let's see whether convective heat transfer is here. So you see this thing called convective heat transfer. If heat transfer OpenFoam, you will be able to see some of these excuse me, some of these ones here. Okay, so this is where the API guide is. You can check out the source code again, but I don't want to go too long into this, but you can see in the source code you'll be able to see what formulas they are using. Okay, so this is where all of this comes from. Okay, so if you take a look at this external wall heat flux temperature, we can also take a look at the header file. Okay, and there should be some description down there on what it's trying to do. So there are three ways you can. Okay, so this is the boundary condition I want to focus on. If you want to look at others, they are under this category called thermal fluid field, fluid thermal models. So under here, you will be able to see a lot of all these boundary conditions. So I will leave it here, or maybe this derived FV patch fields is a bit more telling of what boundary conditions you can use. So yeah, moving on. There are three ways again. You can run this. You can run it using a power heat. A power value. How to say? You can specify the total amount of power that's being transferred to the fluid in terms of heat, or you can actually specify a heat flux, which is in watts per meter square. Okay, you can also specify a heat transfer coefficient with an ambient temperature. So these are the three modes. See, fixed power. You put in a fixed power supply Q into the fluid, or you can have fixed heat flux, or you can have a fixed heat transfer coefficient. So the one I'm using here is a heat transfer coefficient where I have an ambient temperature, and I have to specify the heat transfer coefficient here as well. Okay, so when I use this heat transfer coefficient here, what's actually going on? Okay, so I'm able, you can see between the fluid and the ambient fluid, I'm able to have several layers of, for example, simulated metals. Okay, so for example, you have you look at this left-hand side here, and this is by Fumiya's blog or something website. So you're saying that you can have a few heat flux. You can have a heat flux through the wall, and the wall will have like differing lengths. Okay, so what you can do, discard this. What you can do is this. Okay, so this is your fluid. This is your fluid, and this is, of course, the green line here represents your boundary condition. So you can specify the thermal conductivity of a layer of thickness here. So this is some K1, and then of course you can specify a thickness L1. All right, and you can do it for multiple layers. All right, so this part is actually the boundary condition. Okay, boundary condition. This part is actually the boundary condition. The rest are just, you know, simulated layers where you can talk about what do you call that? They're simulated layers, mathematically modeled to represent some sort of thermal resistance, where your heat flux is either going in or out. So outside here, when you specify TA, or the ambient temperature, that will be the ambient temperature, and then of course you can have a H over here, a heat transfer coefficient between this this surface and the ambient temperature. So you have a T surface minus TA, okay, times H. That will be equals to the Q, heat flux. So there are two things you can play with. One is, of course, you can play with the thickness and thermal conductivity of the layers here. And the other thing you can play with is the heat transfer coefficient between this surface temperature and this ambient temperature. Of course, you can make this thermal conductivity high and this length very low. But I mean, in a case of a heat exchanger, you want to make sure that thermal conductivity here is low because you're trying to insulate this whole thing. So you can simulate that even. Okay, so how do I type this out? Well, if you're not sure, you can always look at the API guide. Okay, there will be a what do you call that? There'll be a template here for you to use. So you can see the thickness layers are specified here. Kappa layers, meaning the thermal conductivity, is over here. You also need to specify a kappa method, which is just fluid thermal. You just leave that one as it is. Don't do anything else. Okay. And again, the mode I'm using here is called coefficient. Value is the internal value. We call it the internal field. So this will be our temperature boundary conditions here. Alright, so the temperature boundary conditions will be for our curved outer shell, the shell N1 and the shell N2. Okay, the rest of them I will just want to leave it as adiabatic. So I'm having the coefficient mode here. The ambient temperature is 293 Kelvin, about room temperature. Thickness layers, I just want to have 2 cm layer of insulation, nothing else. Okay, so where did I find these values? They are from this site FAO blah blah blah.org. Okay, so you see a lot of links in this video because I reference a lot of links out there. Alright, so over here you can find the typical values of insulation. So give or take, you look at this thermal conductivity here. You have type blah 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 insulations. The thermal conductivity is around 0.04, as you can see here, on that order of magnitude. So for example, if you have this expanded cork slab, this thermal conductivity will be in 0.04 watts per meter per degree C, or watts per meter per Kelvin. So that's what I'm using here, 0.04, and that's where I get my value from. Okay, and the typical heat transfer coefficient between air and the surface, it won't be very high. You give or take, it will be around 20. Okay, so you give or take, this heat transfer coefficient will be around 20. If you want to look at that, heat transfer coefficient, air, typical value, you just Google that. You should be able to see in Wikipedia or even in Engineer's Edge. So I prefer to use Engineering Toolbox. That's a very, very good way of doing it. So you see this air, okay? See this air. When you have air to let's say cast iron or mild steel, the heat transfer coefficient will be on the order of 10 to 20, or over here it's like 5 or 8, that kind of thing. Alright, so this is the typical value you will find. For steam, it's like closer to 20, as you can see here. If you look at the Wikipedia, you will find values of 10 to 20, as you saw there. Okay, let's take a look at some typical values. Okay, so some typical heat transfer coefficients include air, where the heat transfer coefficient is about 10 to 100. So if we are talking about ambient air going around this tube, a heat transfer coefficient of 20 will be about there, given this value. So this is one interesting boundary condition you can use to explore heat loss to the environment. So you can actually simulate that with an appropriate heat transfer coefficient and a plausible estimate for an insulation layer being around your shell. So you can actually simulate a little bit of that. Okay, sorry. So the other parts I kind of just make it adiabatic because what we are seeing here is this shell part. You see that there's this curved surface area. which is over here, and let's see the group of faces. I want to see this inlet shell curved. Yeah, so you can see the highlight you can see here. That I have to decide a boundary condition for this, right? For this highlighted part you see here. What happens is that, okay, the way that we actually put this boundary condition, it assumes that the surface is actually 1D. Okay, you don't assume 3D surfaces, right? You don't assume 3D surfaces. So I have to delete all of this. Okay, and then I'll roughly show you what's like. So we have, in actual fact, we have a cylinder shape. Okay, and then we assume that at the boundary, okay, what OpenFoam will do using this boundary condition, it will treat it as if it's a 1D surface where you have T fluid here and the T ambient here, and then of course you have your layering. Okay, it will treat this whole thing as if it were a 1D case at the surface. So it's not a cylindrical case, but you treat it as if it was 1D, and that's what mathematical formula they will be using. Now, if you have these two extended pipings here, for example, and then you have some insulation here and some insulation here, okay, so some insulation here and some insulation here, okay, if you apply this same boundary condition throughout for this curved part, okay, for this curved part on top, okay, it will be as if you'll be treating this part as a 1D case. You'll be treating it as if there's a 1D layer of insulating foam surrounding this surface. And of course we know that's not true, because if you look at this setup, if we were to put a layer of insulation around this tubing, okay, if you were to put a layer of insulation around this tubing, the length of insulation, I mean, from if you look from the cross section, so this is your cylinder, and this is your tubing that's going. You're looking down into the tubing. If you actually surround this whole thing with insulation, okay, this tubing will actually experience a very, very thick layer of insulation, and it's not a 1D case anymore. Okay, you cannot use a 1D case. I mean, you can't use a 1D thickness of 2 cm. It just doesn't work. So I left it as 0 gradient to mean that it's adiabatic. So that's how I kind of approximate things there. Of course, I can make that layer very thick, but again, that layer of thickness for insulation is not very uniform anyhow, because the surface is curved, and the thickness actually from this edge to this end is actually thinner than, let's say, the thickness from this edge all the way to this other end here. So these are just some simplification I made to this model. So alright, so that's why I left the inlet and outlet shell as 0 gradient. Okay, inlet shell will be fixed temperature boundary condition. Okay, then you have the outlet shell, the shell outlet being a 0 gradient boundary condition, and then of course you have your mixed boundary condition here. Now for epsilon k and everything else, they're pretty straightforward. You just have turbulence modeling at the wall, where you have your wall function. So every single patch where I name it wall will be using this epsilon wall function here, and that will include the shell to copper, because this is supposed to be a wall boundary condition. Except you don't say that this is a wall boundary condition over here. Reason being, it's supposed to be a baffle mixed boundary condition, turbulent temperature coupled baffle mixed. So this is supposed to be a boundary condition, but you can assign a wall function to this boundary condition as well, no problem. Okay, OpenFoam knows how to take that in. Alright, then you have calculated for inlet and outlet shell, because you're using a k omega SST kind of class of models here. So this one you don't really have to care too much. What's more important here is this k. Alright, this k boundary condition. Okay, so again we use a wall function. I use a KQR wall function here for all the walled surfaces. Inlet shell, I'll use this turbulent intensity kinetic energy inlet, because this is a pipe flow after all. Well, it's not exactly a pipe flow, but it's something similar. Okay, and all you need to do is just to specify the turbulence intensity. And intensity can be estimated by 0.16 times Reynolds number to the minus 1/8 power. So that will roughly give you the turbulence intensity. I just used a rough intensity of 0.047. There is not too much over there. Okay, and again, I discussed it before in my turbulent not turbulent, OpenFoam intermediate series. So I'm not going to repeat the whole discussion over here. Okay, PRGH, I've already discussed this. Rho, I've already discussed this. This one doesn't you don't really have to worry too much about it, because all of this is calculated, and your density is actually specified by your your density is actually specified by what you need to do is I mean for this boundary conditions, epsilon you don't really have to care too much. K, you kind of need to worry a little bit. Not worry a bit, just be mindful. Okay, these two I've already explained. Pressure I've already explained. Rho, I was saying, yes, I kind of lost my train of thought there. Rho is just the density, but that will be calculated based on your thermophysical properties. So all you have to do is kind of supply an initial value, and you just tell it that it's calculated. Any initial value will be okay. I mean, as long as it's like not zero, that where it can cause numerical instabilities. Now again, I'm almost done here, so just bear with me a little longer. Okay, so what we have here for omega is we have this omega wall function again at all wall surfaces. Alright, process for any what do you call that, parallel boundary condition, we use the boundary condition type of processor. And for the inlet, we use a turbulent mixing length frequency inlet, because this is a turbulence frequency. Okay, so again, please go and watch my intermediate video series. I explain all of this. You just need to specify a mixing length, that's all over here. And the mixing length estimate, you can go to this website over here by sim scale. Alright, and the formula provided is hydraulic diameter times 0.07. Okay, so this is the inlet shell boundary condition I use here. I'm not going to elaborate too much on this. Outlet shell, I'll just use an inlet outlet boundary condition, which is essentially, it acts I think more or less like a zero gradient boundary condition. Except for reverse flow, then it will apply some fixed value. Okay, alpha T, you have this compressible alpha T wall function. Okay, otherwise everywhere else it's calculated. Similar idea for nu T, where everything else is calculated except for the wall parts, and that is the shell region. Okay, so I'll stop for now, and I'll see you guys next time.